Hello everyone and welcome to the chapter of alcohols, phenols and ethers. In the previous section we have completed with respect to the phenols. Now it's time for the ethers. So when we speak about the ethers, now ethers are those particular compounds which are obtained by replacing one hydrogen atom out of the hydrocarbons, either by an alkoxy group or by araloxy group. Let us understand what this particular statement means. So, when we take a look at ethers, let us take into consideration of a hydrocarbon over here. Let me represent the hydrocarbon as RH. Okay, so whenever we replace this particular hydrogen in a hydrocarbon by an alkoxy group, let's say alkoxy group, that what we are going to add is OR dash. So OR dash is our alkoxy group. Okay, so what we get? This particular hydrogen is being replaced by this group, eventually ending up giving us a product ROR dash. So this one is the ether, wherein what we had over there was an OR group has substituted the hydrogen. So therefore the OR group is nothing more than an alkoxy group. So the alkoxy group, when it replaces the hydrogen, it ends up giving us an ether. Of course, we can also prepare the ether from the hydrocarbons. Let us take one more hydrocarbon over here. When we take an hydrocarbon, this hydrocarbone's hydrogen is going to be replaced by an aryl oxy. When we speak about an aryl oxy, let us represent that with OAR. Now, aryl oxy, aryl systems, AR refers for the benzene type of system. Okay, so what is going to happen? The aryl group, the aryl oxy group, is going to come and substitute this hydrogen. So the moment it substitutes the hydrogen, what we get? Hydrogen is being substituted by this group, so therefore we are going to get over here ROAR. Correct. So another ether is formed. In this particular case, the ether is with a benzene type of system or aromatic type of systems. So these are the ethers. So therefore, an ether is a compound formed wherein the one of the hydrogen atom in hydrocarbons is going to be replaced either by an alkoxy group or aryl oxy group. The ending product what we get are ethers. Right? So let us write over here OAR is nothing more than an aryl oxy group. Right? Now, moving further, when we take a look at the structures, when we observe the structure, a particular ether contains the main atom as an oxygen. The oxygen has 4 pairs of electrons. Out of 4 pairs of electrons, the 2 pairs of electrons act as the lone pair of the oxygen, while the other 2 pairs are used for the formation of the bonds or used for the sharing. So therefore, this particular things are going to be connected to the different groups such as alkyl groups or the aryl groups. For a moment, let us take over here that we have the 2 alkyl systems connected to an oxygen. Correct. Now oxygen over here is sp3 hybridized. This particular oxygen, of course, is going to contain a lone pair. It contains lone pair of electrons, while these particular things will show us the shared pair of electrons. Now, the arrangement, when we speak about the arrangement, this arrangement is a tetrahedral. It is a tetrahedral shape, or you can say as an arrangement. Now when we speak about a tetrahedral arrangement, then it is a tetrahedral arrangement. So when you take a look at the bond angles, the bond angle for a tetrahedral arrangement should have been around 109.8 degree. But here, because of the repulsion between the bulkier alkyl systems or the bulkier groups, this particular angle increases. It increases up to 111.7 degrees. So the angle, the tetrahedral angle over here has increased up to 111.7 degrees. Right? So the arrangement over here, what we have is a tetrahedral arrangement. We have the two bulkier groups. Because of the repulsion between the two bulkier groups, this particular angle increases. Oxygen is sp3 hybridized. It has two lone pair of electrons and two shared pair of electrons, which are utilized in formation of the bond. Because of the repulsion, the particular bond angle increases. Right? So let's move further. As we move further, we'll try to understand the types of ethers. Now ethers generally are classified into two categories. One is the symmetrical ether and the another one is the unsymmetrical ether. So generally we represent these ethers as what? R, O, R. Correct. Now in case if both the alkyl systems or in case if both the aryl systems are same, then we classify them as the symmetrical ethers. Now, when we take a look at the symmetrical ethers, what we understand there is, if we want to name them like CH3O, CH3, common name, okay, common name, we call it as a dimethyl because we have two methyls over there. So common naming will become as a dimethyl ether. Right? Now, if we go for an IPAC naming for the same one, then we need to consider oxygen with either one of these particular alkyl systems. So therefore, it is going to become as methoxy. Right? So consider this one with one of those systems, oxygen with one of those particular alkyl systems, so it becomes as a methoxy. What remains behind is a methyl group. We name it as a methyl. Okay, we name it as a methane over there. So therefore, it becomes as methoxy, methane. Right? So it is going to be as a methoxy methane. Next, if we take into consideration of C2H5O, C2H5. Now there are two ethyl systems, so it will become as diethyl ether. Two ethyls, so therefore diethyl. It's an ether, so we'll name it as an ether over here. That is a common name. While when we take a look into an IPAC name, take the oxygen with one of these, so it will become as ethoxy. This is an ethyl group, so it becomes as an ethane. So it will become as ethoxy ethane. Okay, so all these particular things, what you are seeing is the symmetrical ether. Symmetrical ether, in short, both the alkyl systems connected to the oxygen should be the same one. While on the other hand, if we take a look into an unsymmetrical ethers, what we need to understand over here is both these particular alkyl systems are not going to be same. Example, let's take over here CH3O, C2H5. Now, when we try to name it to a common nomenclature, then we need to go alphabetically. For example, this is N, methyl, this is ethyl, E. So, ethyl, methyl, ether. Okay, so this is ethyl, it starts with E. This is methyl, it starts with M. So, therefore, it goes as ethyl, methyl, ether. This becomes a common name. When you go through an IPAC name, you need to be very careful there. That is, you need to understand the smaller section of these and you need to take it with the oxygen. So eventually the smaller one out of methyl and ethyl is the methyl group. So the methyl group has to be attached with oxygen. Thus, it is going to become as methoxy. This particular thing, what we have is an ethyl group. It becomes as an ethane. So what we have here is methoxyethane. Alright. Going further with the next one. Let's take one more example. A benzene type of system connected oxygen with CH3, commonly called as anisole. Okay, now when we take a look at its IPAC name, so the IPAC name is going to become as, in this case, again, oxygen goes with the smaller one. Smaller system is CH3. So, methoxy benzene. This is how the entire thing goes by. Alright. So, we have two categories. One is symmetrical, the another one is of course the unsymmetrical ethers. Now, let's take a look into, as far as possible, into the modes of preparations. We have several types of preparations, several methods of preparations of these particular ethers. So, when we take a look at preparation of ethers, the first method is by dehydration of alcohols. Okay, so first one is by dehydrations. Dehydration of alcohols. When we take a look into dehydrations, okay, that means we are going to take an alcohol, treat this alcohol with protonic acids. Protonic acids, such as what we have is H2SO4, is H3PO4, right? So when we treat these particular alcohols with concentrated protonic acids, we get ethers, but it all depends upon the reaction conditions. The reaction condition is more important over here. Now, let's try to understand that. If I'm going to take over here two molecules of C2H5OH, okay, and this particular thing is treated with concentrated H2SO4 at 413 Kelvin. If we are going to take this particular condition into consideration, then it will yield C2H5O C2H5, that is diethyl ether is obtained. Now, the same condition, if I am going to take over here, that is C2H5OH. And now, if I am going to react this one with concentrated H2SO4, provided the temperature is 443 Kelvin. At this particular temperature, what is going to happen is this particular alcohol loses water. How does it lose its water? Is that this particular OH takes hydrogen from one of the carbons, leading to the formation of C double bond C, H and H here, along with elimination of water molecule. So, it will yield an alkene. So, whether you are going to get an ether or whether you get an alkene, it all depends upon reaction condition. At lower temperature, we are getting over here ether. At higher temperature, that is, as the temperature goes on increasing, this particular alcohol ends up giving me an alkene. Basic information, what you need to understand is, whenever we react an alcohol with the protonic acids, the temperature plays a very significant role. Higher temperatures will yield alkene, lower temperature will yield ether. Right? Thank you. We'll move forward. Observe the entire mechanism. This particular mechanism, that is of the dehydration of an alcohol, occurs in 3 important steps. So, this is a mechanism for the reaction of 2 molecules of C2H5OH, which is going to, of course, react under the presence of concentrated H2SO4 at, if we take into consideration of the temperature as 413 Kelvin, what we have observed is it is going to yield the ethers C2H5O C2H5. Right? So, what we have here is an ethanol, and what it has given us is ethoxy ethane. We can either have an ethoxy ethane as a name, or we can call it as a diethyl ethers. This particular mechanism is going to contain 3 major steps. The first step is the step of protonation. Alright, so step number 1. Step 1 is going to be protonation. Protonation of alcohols. Okay, so let us take into consideration of an ethanol, that is C2H5OH. This ethanol is going to get protonated by hydrogen, that is proton. It reacts over here. This is a way how the oxygen is going to attack the proton, eventually yielding us C2H5OH and H over here. So this is the oxygen with a positive charge. Correct. Now, step number 2. In step number 2, the unprotonated alcohol is going to attack on the protonated alcohol by a nucleophilic substitution. Okay, so it is going to undergo a nucleophilic attack. Therefore, the second step is nucleophilic attack. Of unprotonated alcohol on protonated alcohol. Okay, so what we are going to get over here is, let us have as CH3, CH2 to H plus, this is an unprotonated alcohol, we'll take, so what we are going to have here is CH3, CH2, OH, H over here, positive charge, right? So now, this is the mode of attack, that is oxygen attacks the carbon, this particular bond breaks. It breaks, giving out or displacing out the water. So when this particular reaction occurs, what we are going to have is CH3, CH2, oxygen with hydrogen. This hydrogen remains here. Okay, this fellow is going to generate a positive charge, and now it is connected to CH2 and CH3 plus what we get here is water. This is the step 2. In step number 3, whatever the oxonium ion, that is oxygen with a positive charge, is present here, it liberates this particular hydrogen. In short, loss of proton occurs. Thus, step number 3. Step 3, the oxonium ion. The oxonium ion loses proton. That is nothing more than deprotonation. So when we have deprotonation, that is CH3, CH2, oxygen with the hydrogen over here, positive charge, CH2 and CH3, right? Now this is going to lose that particular proton. When it loses the proton, it does by giving the electrons to the oxygen, thus giving rise to CH3, CH2, CH2, CH3. Thus, what we have is the ethoxy ethane. Right? So, this is a mechanism what you can expect about the deprotonation of an alcohol to give rise to ethers. So far, we have seen the mechanism of the dehydration of alcohols in order to yield the ethers. If we go through the dehydration, the method of dehydrations, the dehydration of alcohols. Now what it was happening was, through this particular mechanism, only the symmetrical ethers were formed, and that is the greatest limitation. So the one limitation that this particular process has is only symmetrical. Only the symmetrical ethers are formed. That's a huge limitation or a huge drawback. On the other hand, we have the next type of preparation, and this particular thing we call it as Williamson's ether synthesis. Okay, so what we have here is the Williamson's ether synthesis. Through this particular Williamson's ether synthesis, we can produce the alcohols which have the substituted alkyl groups also. Let's try and understand first. In the Williamson's ether synthesis, we usually use a simple alkyl halides. Usually preferred is the primary alkyl halides. Okay, so what we have here is the alkyl halides. These alkyl halides are reacted with sodium alkoxide. Okay, now this is sodium alkoxides. Now when this particular reaction occurs, right, so when this particular reaction occurs in the presence of the diether, the halogen and sodium are eliminated. In order to give the byproduct, we get the byproduct that is NaX. Right? So, along with this, what remains behind is the alkyl system connected to the oxygen. This is further connected to the another alkyl system, where both the alkyls can be same or they can be different, giving rise to the main product that is the ethers. Right? Now, let us understand using few examples. In the first example, let us consider that we have C2H5 Br plus NaOC2H5, that is sodium ethoxide. When this particular reaction occurs, what we already understand from the general reaction is that the combination of sodium and hydrogen occurs, leading to the formation of NaBr as a byproduct. Along with this, C2H5OC2H5, that is the ethoxy ethane is formed. Now here we have observed the formation of a symmetrical ether. Let us go one step further in order to understand how an unsymmetrical ether can also be formed. Okay, in order to go forward with that, let us take into consideration of CH3, CH3. Now here O and A. Right? Now, Let us take a highly substituted system. Now this is nothing more than sodium. Okay, 1, 2, 3, 4, tertiary butoxide. When this particular thing is going to be reacted with, let us say that we have a bromine over here connected to CH3. Okay, now what happens is the oxygen attacks on this particular carbon, because carbon and bromine, this particular bond develops a polarity. A polarity wherein the bromine is more electronegative. So therefore, the electron density shifts over here, giving rise to a delta positive on carbon. Therefore, the oxygen attacks with this carbon. When it attacks to this carbon, what happens is sodium and bromine. Bromine goes out as a good leading group. Bromine attaches with sodium, giving rise to NaBr. This is a byproduct. Now, what happens next is CH3, CO here, CH3, oxygen with CH3. Right? Now here, let's try to understand the impact nomenclature. Let us select the longest possible carbon chain, and that is this. At the position 2 I have methyl, at the position 2 I have methoxy, OXY. Okay, so it becomes as 2 methoxy first, 2 methoxy, 2 methyl, 2 methoxy, 2 methyl becomes as propane. Okay, this is how the entire reaction occurs. Now, what if we reverse the condition? Reversing the condition, in a sense, if we are going to take the particular alkyl halide as more substituted. More substitution, in a sense, either if I take a secondary alkyl halide or either if I take a tertiary alkyl halide. Let's observe what happens. So, in that particular condition, let us say we have CH3, CH3, Br. Correct. 2 bromo, 2 methyl propane. Now this thing is going to be reacted with sodium methoxide. Sodium methoxide, 2 bromo, 2 methyl propane. Now, whenever we either take secondary, remember this, whenever we either take secondary or whenever we take a tertiary alkyl halides, here, due to the steric hindrance, the elimination is favored more. So therefore, rather than this particular thing attaching, what happens is, here the elimination occurs. Elimination, in a sense, this particular CH3O takes 1 hydrogen from this. When it takes 1 hydrogen from this, sodium and bromine, of course, these particular things are going to get combined in order to form NaBr. Bromine goes taking the electrons, right? Now, once this particular combination has done, CH3O, oxygen comes, takes a proton from here. That means hydrogen leaves, giving the electrons. Now, this is a carbon which generates positive charge. This is a carbon which generates negative charge. So, therefore, a double bond is created between this carbon and this carbon, giving rise to CH3, double bond CH2. This is the condition what you get, plus this thing forms CH3OH. So therefore, an alkene is obtained. Therefore, what we understand is, whenever we have tertiary systems or whether we have secondary systems, at this particular condition, what happens is the elimination is more favored. So here, elimination is favored in this condition, right? So this was about the Williamson's ether synthesis, whereas wherein we take alkyl halide, react the alkyl halide with sodium alkoxides, leaving, it is going to give us a product as an ether. Correct. Now, usually the product is obtained more if we have the alkyl halides as primary alkyl halides. That's a key point. Right? So, let's observe the next one. So, in the next case, we will see how the phenols can be converted into their ethers. So, in the next case, about the phenols, conversion of the phenols into ethers. Alright. So, it's a basic simple phenomena where we take phenols, react this particular phenol with sodium hydroxide. When we react this one with the sodium hydroxide, of course, we get an intermediate which is sodium phenoxide. The sodium phenoxide is considered as a phenoxide moiety here. Okay, so let's first take this particular thing till the phenoxide moiety. So, in the first case, what we do is we take the phenols. These phenols are going to be reacted with sodium hydroxide. So, let's take over here sodium hydroxide. Now, when it reacts with sodium hydroxide, it will give rise to sodium phenoxide. So that is O and A. So sodium phenoxide. Now sodium phenoxide in this particular case is considered as the phenoxide moiety. It is considered to be as phenoxide moiety. Now this particular moiety is an intermediate. It will react with the next molecule, a particular molecule of alkyl halides. So when it reacts with the molecule of alkyl halides, let's take Rx, right? Now that means the oxygen over here is going to react with alkyl system. So the moment it reacts with the alkyl system, sodium connects itself with halogen in order to give sodium halide. So what we have here is the benzene system with oxygen. Now oxygen is going to get connected to R. So in short, what we have got is an ether. Ether is obtained from phenol. This is how the entire reaction is formed. The byproduct over here and AX. Right? Now, let us see as how can we create the ethers from alkyl halides. Alkyl halides reaction with dry silver oxide. Okay, so the next one is reaction with dry silver oxide. So when we take a look at the reaction with the dry silver oxide, first thing that we need to know here is, let's take into consideration of alkyl bromides. So I will take into consideration of two molecules of alkyl bromides. Now, this thing is going to react with dry silver oxide, that is Ag2O. Now, please understand the representation. I'll take one oxygen over here. These are the bonds. This is Ag here, this is the another Ag here, right? So, when this particular reaction occurs, this bromine and this particular silver gets connected, this particular bromine and this particular silver gets connected. What remains is this carbon gets connected to this oxygen, this carbon gets connected to the oxygen over here. In short, it's going to give us CH3, CH2, oxygen, CH2, CH3 plus what remains is 2AgBr. Correct. So it has given rise to diethyl ethers along with the silver bromide. So these are the two reactions as what we have completed now. Let's proceed further with one more important reaction, that is preparation of an ether from Grignard's reagent. So preparation of ether from Grignard reagent. Alright, so let us take into consideration of first over here as CH3O CH2Cl. Okay, now this is chloromethoxymethane. This is how it goes. Chloromethoxymethane. Okay, so therefore this is chloromethoxymethane. When it is reacted with, let's take a Grignard reagent such as methyl magnesium iodide. Okay, so now what happens here is this methyl section replaces chlorine. It comes over here, it takes this particular chlorine out. So the moment it takes that particular chlorine out, that means it is going to form over here CH3O CH2 CH3. This is nothing more than the methoxy ethane plus this thing has replaced this particular chlorine. Now chlorine will come over here in order to give rise to NgClI. This is the byproduct as what we obtain, right? So this was about the preparation of an ether from Grignard's reagent. Let us proceed further in order to understand about the properties. The properties of ethers. Now, when we take a look at the ethers, ROR, the ether functional group is the one of the most least reactive among all the functional groups available. Now, due to this least reactivity, the bonds are not easily cleaved. Easily cleaved in a sense, the bonds are not easily broken. Due to which a drastic condition has to be applied. So over here, what we understand is, it requires drastic conditions in order to undergo reactions. Let us try to understand the first one, that is the cleavage. The cleavage of OR bonds. Okay, so the cleavage of OR bonds, the breaking of those particular OR bonds. Now, if we take into consideration of R, O, R dash, let's take it here as dash, that is for the ethers. Now, ethers will react with one molecule of hydrogen iodide, provided the condition is drastic. Drastic in a sense, higher temperatures are required. So therefore, we would require over here 373 kelvins. When we apply 373 kelvins over here, the alkyl and iodine gets attached, giving rise to R-R. Alkyl iodide plus an alcohol alcohol is obtained. Now this alcohol, that is nothing more than a mixture of alcohol and alkyl iodide are obtained, of course. Now this particular alcohol further undergoes the reaction with the hydrogen iodide if it is taken in excess. Thus ROH plus another molecule. Now again, what happens is this hydrogen combines with OH, giving rise to an H2O plus this alkyl system, and this particular iodide gives rise to RI, that is the alkyl iodide is obtained. Right? So this is how the entire reaction follows up. Understand about the mechanism. So when we take a look at the mechanism of this entire process, right? So in this particular mechanism, it consists of the 3 steps. This mechanism, let's take into an account for an example of CH3O C2H5. Right? So plus hydrogen iodide. Let's see as what we are going to get the answer for this. So eventually this is a reaction wherein we are taking a look at the cleavage of oxygen and an alkyl systems. As I said, that this entire process is going to have 3 steps. The step number 1 is protonation. Protonation to form oxonium ion. Okay, so when it is going to form the oxonium ion, let's observe that. So CH3O C2H5 plus HI, right? So oxygen attacks the hydrogen, giving rise to a particular intermediate, that what we have is CH3, oxygen, hydrogen over here, oxygen generates a positive charge, C2H5. This is nothing more than the oxonium ion, right? So oxonium. Now, iodine is a good leaving group. In step number 2, we will see that the iodine usually attacks that particular carbon which is less substituted. Okay, so therefore, in the step number 2, as iodine is good leaving group, it is a very good leaving group. So therefore, it is going to attack to that particular carbon which is less substituted. That means when we have an oxonium ion over here, CH3, oxygen, hydrogen, over here C2H5. Now it will choose that particular carbon which is less substituted. That means it is going to, of course, attack this particular carbon. Thus, when iodine attacks to this particular carbon over here, an intermediate is formed. Okay, so therefore what we have is the intermediate CH3, oxygen, here is what we have as hydrogen, this is connected to C2H5. This thing breaks over here, this particular intermediate breaks over here, leading to the formation of CH3I plus C2H5OH. Now, when this particular thing comes to our step number 3, now usually what happens is this reaction ends over here. In case if we have an excess amount of hydrogen iodide, then the alcohols also start reacting with your hydrogen iodide. So therefore, here, in case of excess hydrogen iodide, what happens is C2H5OH. It starts reacting with hydrogen iodide in order to give rise to. Now, This particular thing attacks over here, that means this particular combination of water is formed, giving rise to CH5I plus H2O. So therefore, this was the entire three-step mechanism for the reaction, wherein it involves the cleavage of oxygen and alkyl group. Okay, so therefore, if we observe that particular reaction over there, we are going to have the first step, that is CH3I plus. We can also have, if we are going to take this one in excess quantity, we are going to have over here C2H5 plus. What we are going to have is H2O if hydrogen iodide is present in an excess quantity. Right. So let's observe the next phenomena. The next phenomena wherein we will take into consideration of the reactions of the phenols. So, in the next case, if we observe the cleavage in the ethers containing the aromatic group, that is, in the systems, something like this, oxygen and alkyl over here, right? So, we have two bonds to take care of. One is oxygen alkyl bond, another is oxygen aromatic bond. Usually, the oxygen alkyl bond is broken. This particular bond is going to be broken because the oxygen and this particular aromatic bond is much more stable. Okay, so therefore, because of the higher stability of oxygen and the aromatic ring over there, when we try to react this one with hydrogen iodide, the bond between oxygen and alkyl system breaks in order to give rise to our alkyl iodides, along with the benzene system having OH, that is nothing more than, it gives rise to phenol. This is ether. So in case if we are using a particular ether containing an aromatic system, the bond between oxygen and aromatic system remains undisturbed, while the bond between oxygen and the alkyl system breaks down. Right? So, when we observe the next phenomena, this next phenomena, let us take into consideration like halogenation. Halogenation using anisole. So, if we consider an anisole here, OCH3, anisole. This anisole undergoes reaction with Br2 under the presence of ethanoic acid. Alright, so under the presence of ethanoic acid, it gives rise to two products. One, of course, is going to be a major product, and another one is going to be a minor product. So, OCH3, and here is where a bromine is going to get attached. This is at the para position, and therefore it is going to be major product. Okay, so this is para bromo anisole plus OCH3 and Br over here. So this one will become as ortho bromo anisole. Right? So this was about the halogenation is concerned. Let us observe one most important thing, the last reaction for the day, and that is the Friedel-Crafts reactions. So what we have here is the Friedel-Crafts reaction. So as we take a look into the Friedel-Crafts reaction with respect to the ethers anisole, okay, we have two cases. One is the alkylation and the another one is the acylation. Let us observe the first one. Let's take into consideration of an anisole OCH3, anisole is going to be reacted with. Let us take into consideration of CH3Cl methyl chloride. That means this particular process is a process of alkylation. Okay, under the presence of anhydrous AlCl3. Now this particular methyl group is going to attach at two positions. Of course, one position is going to be the ortho and the another position is going to be the para. Thus, what we have here is OCH3 and CH3 group over here, giving rise to ortho methoxy. Now this particular position with respect to CH3 is a methoxy. Okay, this particular position is an ortho of a methoxy group. So ortho methoxy toluene. This is minor product, while the another one, what we have is OCH3, and this is where the another CH3 comes. So this one is going to become as para methoxy toluene. Right. So we have these two products, and this particular reaction we consider it as alkylation, Friedel-Crafts alkylation. Going further, if we take this particular anisole and as we move further to the another set of reaction wherein let us use acetyl chloride. So this particular process under the presence of anhydrous AlCl3. Now this particular process, what we are going to write down is going to be the Friedel-Crafts acylation. The first one was Friedel-Crafts alkylation. Now it's going to be the Friedel-Crafts acylation. So, in an acylation process, what we have here is CH3. The first one, this particular one, this one, connects at the ortho position, giving rise to CH3. Thus, what we are going to have is orthomethoxy. This particular OCH3 is ortho with respect to this. So it will become as orthomethoxy acetophenone. Right? Now this one is an ortho, so it is going to be minor product. Remember, the minor product is obtained because of the steric hindrance. While going further, this is our OCH3 group, and this is where C double bond O CH3. Okay, now here is where I get para position of this particular methoxy. So para methoxy. What we have is acetophenone. This one, on the other hand, is going to be the major product. I hope the entire sequence of the reactions are well understood. Thank you for your time. Take care.